Hello everyone, welcome to the presentation of the team 1001. We are Khang Nguyễn Hoàng, Quân Đỗ Hữu, Nguyễn Nguyễn, and we are advised by the coach Vũ Đỗ Huy Cường. And today we will talk about problem A, which is about hair pulling to layer nest. So before getting into our model and showing what we were trying to achieve, we will start with a little background observed from nature. In some bird species, sometimes we observe that they have a very special behavior. They tend to approach different mammals, for example, like dog, cat, or even human, and they pull the hair or fur out of mammals and use that hair to build a nest. So this behavior is observed widely across the world, but there's empirical evidence that in area with a higher latitude, which means that those areas are significantly colder. So the birds tend to go snatching the hair more likely and more often. So our objective in the project is that we want to build a model that can explain this behavior by explaining how this behavior can benefit the bird. For example, like how increase the survival rates of the population, especially in colder temperature. So before getting into our model, we will try to make some assumption about the bird species first. And these assumptions are based on the collected information of the relevant papers. So some of them we think of that is logical to assume. And first of all, we assume that the maximum lifespan of the bird species is 3 years, which means that all the birds of age 2 will die in the next year. So and we assume that the birds mature and reproduce up to 1 year, and in 1 year, there's only one breeding season. And next, we want to focus on only one thermal benefit of the hair snatching. So as well, we want to assume that the insulating value is the primary benefit of using the mammal's hair. Next, based on many readings, we come to assume that the birth optimal temperature is 38 Celsius degree. And this is also the optimal temperature for the bird nest. And finally, we're going to assume that the temperature of the environment will only affect the death rate or the survival rate, but impose no change on the birth rate of the species. And now we come to construct our model. The main objective that we met before is that we want to understand how hair snatching could benefit against the harshness of the temperature or the survival of the bird population. So to understand this, we need to take a look at how the birth rate and the survival rate of the species are affected by this behavior and the temperature. So for our model, consider these rates. First of all, we consider the natural birth rate of birth at HI, which we know as FI0. And we also consider PI0, which is the natural birth survival rate from HI to HI plus 1. And we want to estimate how this rate change due to the hair snatching in regions with a different average temperature. So we want to estimate the FI, which is the real birth rate of birth at HI, and the PI will be the real survival rate from HI to HI plus 1. And these two rates will depend on the temperature. So now we come to see the relationship between the rates. First of all, because we previously assumed that the temperature and the hair snatching behavior do not affect the birth rate. So the birth rate will be the same for all scenarios that we consider. And when there is no hair snatching, the survival rate, we can expect that the temperature gets colder. Without hair snatching, the bird will lose the thermal benefits and they face the higher risk of dying. So this risk could increase when the temperature decreases. And to estimate that, we multiply the natural survival rate with a linear factor depends on the temperature gamma. And you can see that this linear factor should be smaller than 1 if the temperature is smaller than 38, which is the optimal temperature. And it would get close to 0 if the temperature becomes smaller. And we have the equation as following. And finally, when there are hair snatching behavior, it means that the birds now tend to collect hair and keep their nest at a constant optimal temperature that would best nurturing the newborn. So in this case, the newborn survival rates increase up to the maximum, which is the natural survival rate. However, for mature birth, they had to go out more and facing the risk of dying when collecting hair. So the survival rate decreased, and we model it by multiplying the previous survival rate with a risk factor smaller than 1, which we denote as R. And this risk factor can depend on the temperature, but for simplicity, we consider it to be the same in different temperature. And now we can ready to model the population. So at the year end, we denote that rho Jn be the number of members at the shade age. And we can see that the number of newborn born at the year n plus 1 will depend only on the number of population of the birth at age 1 and 2 in the year n, because we assume that the birth rate at age 0 cannot give birth to the other. And we can see that then we have this equation, and based on the birth rate f1, f2 corresponding to the 2 different ages. And then if the birth rate HI plus 1 in the year n plus 1, it will depend on the net population of the birth rate HI in the year n, and also the rate changing from HI to HI plus 1. So we have the two equations lower. And so equivalently, we can see that this system equation can be rewritten as this matrix multiplication equation, where the vector rho n and rho n plus 1 will correspond to population distribution of the ages, and the matrix A will consist of some zero and the birth rate and the natural survival rate. So now we come to solve this equation. And know that the A is a non-singular matrix. We know that this the solution of this equation, the rho n, will then converge to this vector C lambda 0 to the n v0, where lambda 0 is dominated. And you can see that this result means that if Pn be the total population of the species at year n, then the total population will increase in infinity exponentially. So after we solving the model, we come to the equivalent constant, and we find the best constant so that our model can have a solution that best fits the empirical data that we have. So these are the constant that we think is reasonable to assume. And then this is a result of our model. So here we demonstrated 4 different plots for the 4 different scenarios correspond to the 4 different average temperature, which are 30, 20, 15, and 10. And in each plot, we plot 2 different scenarios of the birth population, which consider when we have no hair snatching behavior and when we have hair snatching behavior. So we can see that when the temperature is high, then you can see that the hair snatching behavior increase slower compared to the no hair snatching behavior. And when the temperature starts to decrease, you can see that now the hair snatching clearly have the benefit over the no hair snatching behavior as the population now increase more rapidly. And you can see that the gap between the 2 scenarios starts to increase more and more when the temperature decrease.
In working on Model 1, we realized that in real life, as a species population grows within a confined environment, members will begin to compete for food, space, and resources. This phenomenon is called overcrowding. The effects of overcrowding include decreased birth rate, increased mortality rate, reduced fitness in each member of the species, etc. We wish to modify Model 1 to more accurately portray this phenomenon and study its effect. That's why we developed our Model 2, which is the density-dependent model. The basic idea is that adding a single new member to the population reduces the birth and death rate by some constant factors. For the birth rate, consider a member of the population with birth rate F. Adding a single new member to the environment reduces the birth rate to F times A for some A less than 1. For a population of size Pn, the birth rate is reduced to F times A to the power of Pn, which is also equal to F times E to the power of ln A times Pn. Similarly, we can derive that for a population of size Pn, the survival rate is reduced to P times E to the power of ln B times Pn. We proceed to modify our Model 1. Instead of keeping a constant matrix A, we update it prior to each year to account for the current population size. Prior to year end, we replace the old Fi terms by the product of themselves with E to the power of ln A times Pn minus 1, which is the effect of overcrowding on birth rate. Similarly, we replace the old Pi terms by the product of themselves with E to the power of ln B times Pn minus 1, which is the effect of overcrowding on the survival rate. This produces a new matrix A prior to each year. The A structure of the next year is then calculated just like in Model 1. That is, it equals to the updated matrix A times the A structure from the previous year. We chose ln A equals ln B equals minus 0.0001. All other constants are taken as in Model 1. This is the result of Model 2 taken over a period of 30 years. In a region with average temperature of 30 degrees Celsius, the species is better off not performing hair snatching at all. This is very similar to what we got from Model 1. In colder regions, however, hair snatching clearly has a significant impact on the population. Thanks to the stability it provides for young birds, the population settles between 1,400 and 1,500 individuals in all cases. Without it, the population struggles to increase in size as the average temperature drops. In a region with average temperature of 10 degrees Celsius, the population size even reduces. We note that the advantage gained from hair snatching in colder region in this model, while very significant, is much less than that in Model 1. This is due to the constraints on population size produced by overcrowding.
Now we come to conclusion. In regions with hot climate, the risk of hair snatching outweigh the thermal benefit. This suggests there are other benefits of hair snatching at play. As the average temperature decreases, the thermal benefits provided by hair snatching increase in magnitude. When results are plentiful, this results in faster population growth and higher overall population size. When results are limited, the thermal benefits help to keep the population relatively stable. This benefit is vital in especially cold areas. This partially explains the increase in the proportion of bird species using hair in their nest as we move from hotter to colder climate. About limitation, our model did not address all the potential benefits. Assumptions regarding the birth rate and the survival rate might not be realistic. The effect of temperature should be more complicated in real life. We could not find enough data to verify the accuracy of our model with high certainty. About future direction, investigate further the effect of other potential benefits and risks. Use more complex models to account for more variables. Focus on one species to reduce variability and improve data access. Acquire more real-life data to better fit the model. And here is some of our results. Thank you for listening.